Okay, this is section 16.6, and it's talking about how to use the instantaneous center of zero velocity. What is that? Well, just real quick, we'll go through it, but let's say we have a wheel on the ground and it's making contact, and we know that the center of mass has some velocity g. That point on the ground is our instantaneous center of zero velocity. And we can figure out that v is equal to omega r if we know v and we know r, then we can find out omega. So it's a clever way to find omega. So we normally have this equation right here where velocity of b is equal to the velocity of a. This is our translational, plus omega crossed r. Well, if we can eliminate the translational portion and find a place where the velocity at a is equal to 0, then we only have a rotation about a. Alright, so we're going to use the fact that the velocity is always perpendicular to the relative position vector from IC to the point, and that's like this thing right here, right? Those are perpendicular to each other. So if we eliminate velocity a, we can just reduce this down to the velocity of b is equal to omega crossed r of b with respect to c, or the instantaneous center. Okay, I'm going to go through several cases. Here's case 1. Check out the book on all these too. Case 1 has something with a circular path. It is some sort of blob. We know about point A, and we know that it has some velocity at A, and we're told that it has some omega. So these two things are important. If we take this velocity and trace this distance r of A with respect to the instantaneous center, that distance needs to be equal to the velocity over omega if we rearrange this formula, right? Oh, I should never write it r omega. I should always write it omega r so we remember the cross product correctly. So if you draw this distance to be VA over omega, this will be perpendicular, and this right here is your instantaneous center of zero velocity. Okay. The second case. We have another blob. This is our rigid body, and we know the velocity of some point A, and we know the velocity of some point B. Alright, so the trick here is just going to be to draw perpendiculars, and where they intersect is going to be our instantaneous center of zero velocity. Alright, so in that case we knew velocity of A and velocity of B, and they were not parallel. They could be the same magnitude in this case. We'll see what happens if they are in other cases. Alright, what if this blob has some horizontal velocity at A, and down here at B it's actually going this direction? Well, first you want to connect A to B. That's our rigid body right there. And then I'm going to connect the arrowheads. Right here is our instantaneous center of zero velocity. So it's rotating about that point is all that means. So in this case we knew the velocities, and that's telling us there's some omega about this direction. Okay, what if our rigid body has A moving as such, and then B is located here, but it's got a little bit longer velocity vector. Well, let's extend A and B, draw a line through them, and let's draw a line through the tips of our velocity vector arrows. Right here, where they intersect, is our instantaneous center of zero velocity. And then you have two different radius. So this would be your R of A with respect to the instantaneous center. This would be R of B with respect to the instantaneous center. And this looks like we would have an omega in the positive direction. Okay, so there's a couple special cases also. Let me flip my notes. What if we have, this could be in 3 dimensions too, right? So that was a little too big of a blob. What if we knew the velocity of A? We also knew the velocity of some point B, and we knew the velocity of some point C. Well, I'm going to try to project these in 3D space properly. Where those intersect is going to be our instantaneous center of zero velocity. So that's a right angle, that's a right angle, and that's a right angle also. Alright, I'm going to do a what if. So what if we have a case where our rigid body, AB, is undergoing a path where they both have a radius of curvature and they are equal to each other. That means our velocity vectors would look like this. In that case, we're looking where the velocity of B is equal to the velocity of A. We can say that no instantaneous center. It is not rotating. This would be a case where the whole thing is just translating at that instant. And, well, at any instant, it's undergoing curvilinear translation, right? There's no rotation. Any other special cases I'm thinking about? Okay, just a quick, what about a rolling wheel? So, have a wheel, it's on the ground. This thing has a center of mass, we'll call G, and it has some velocity of G, and it is rotating with some omega. If we know R, we can also figure out what R of G, sorry, not capital R of G with respect to the instantaneous center is, because our perpendicular is giving us an instantaneous center right here. Remember a couple videos back, I think I talked about how the velocity was 0 at that instant. We can prove it mathematically too. If the velocity of point G, is equal to omega crossed R of G with respect to IC, and omega is in the k-hat direction, and R is in the positive J. I'm going to get a velocity of G equal to positive R omega. and that's something we discovered before. Thank you.